Antarctic region. Before the IP, a three-dimensional seismic velocity structure of the Antarctic plate had been investigated by surface wave tomography using the shallow earthquakes that occurred at the plate boundaries and the surrounding plates. The utilized seismic data had been compiled in the Data Managing System, DMS, of the Incorporated Research Institutions for Seismology, IRIS, as the stations belong to FDSN. For instance, the seismic travel time tomography beneath the Erebus volcano of Ross Sea, near MCM, see Figure 1 of Chapter 1, indicated the existence of a remarkably low velocity anomaly associated with hot spots, which originate from the volcano. The average thickness of the continental crust of East Antarctica was 10 to 20 kilometers larger than that of West Antarctica. The corresponding lithosphere of East Antarctica posed high-velocity layers down to a depth of 150 kilometers. Moreover, an investigation by body wave propagation within the upper mantle of East Antarctica revealed the presence of a strikingly low-velocity anomaly in the 200-kilometer depths underneath the lithosphere. In order to explain the velocity models derived from both the observed and theoretical waveforms, the presence of the unique chemical composition and thermal gradient for the depleted mantle was required, which characterizes the Archean age in the Earth's history. Moreover, a three-dimensional seismic velocity model of the upper mantle beneath the Erebus volcano of Ross Island was derived by travel time tomography using the data from the Transantarctic Mountain Seismic Experiment, TAMSICE, 2000 to 2002. The low-velocity region corresponds to a hot plume of the volcano that continued from the surface of the Earth to the 410-kilometer seismic discontinuity. During the IP, the total number of seismic stations was remarkably increased within the Antarctic continent by conducting several geophysical projects. As introduced in Chapter 2, obtaining data from the Antarctica's Gamburtsev Province, AGAP, of the Gamburtsev Mountain Seismic Experiment, GAMSICE, Figure 1a, and the Polar Earth Observing Network, POLNET, the space resolution of the Earth's structure by seismological research had been significantly improved. The crust and upper mantle structures beneath the wide area of East Antarctica with the cinder at the Gamburtsev subglacial mountains, GSM, were precisely achieved by phase velocity analysis using the waveform data obtained from a gap. The shear wave velocity of the Precambrian cratons, continental blocks, at the inland plateau of East Antarctica represented an intermediate velocity model between the high-velocity structures that appeared at the Slave Province of Canada in the Yilgarn region of West Australia and the relatively low-velocity regions such as that of the Northeast Craton in the mainland China. The lithospheric age down to a depth of 250 kilometers under GSM was revealed to be early Proterozoic, or late Archean, compared with that under the other globally distributing continents. Moreover, the crustal thickness of GSM was found to be more than 55 kilometers thick. This was comparable with those determined by body wave tomography and receiver function analyses. A. Map of the AGAP GAMSICE seismic array, overlaid on the bedrock topography from BedMap 2, modified after. The blue and white triangles indicate the location of seismic stations provided by the United States and Japan, respectively. Abbreviations are as follows: GSM, Gamburtsev Subglacial Mountains, VSH, Vostok Subglacial Highlands, PSB, Polar Subglacial Basin, and WSB, Wilkes Subglacial Basin. Copyright Clearance Center, CCC, http://www.copyright.com/ License number, 4,278,571,127,723, License date, January 30, 2018. B. Horizontal slices through the P-wave tomography model of the upper mantle structure beneath central East Antarctica by using the AGAP data, at the depths of 150, 200, 250, and 300 kilometers, respectively, after. Each slice shows the 0 meters gray, and 1000 meters, tan, contours from BedMap 2. Abbreviations are the same as in A. Copyright Clearance Center, CCC, http://www.copyright.com/ License number, 4,278,571,127,723, License date, January 30, 2018. Seismic travel time tomography by using body waves obtained from a gap demonstrated the existence of a high-velocity region in the upper mantle depths beneath the wide area including GSM, Figure 1b. The evidence suggests the presence of the thick lithospheric root under the East Antarctic continent. However, there are also horizontal variations in high-velocity layers within the depths of 150 to 350 kilometers. Therefore, conducting additional analysis in relation to the geological formation process of the mantle structure under the continent is required. The upper mantle isotropy of the wide area of East Antarctica was investigated by shear wave splitting analysis adopting the teleseismic SKS waves recorded by a gap. A space distribution of the fast splitting orientation for shear waves suggested the presence of several subtectonic terrains characterized by different orientations of the isotropic axis within the studied regions of a gap. Particularly, beneath and around GSM, identically different results were achieved as the fast polarization orientation in shear wave isotropy. A local difference in the isotropy was assumed to be affected by several candidates of geoscientific information, such as the seismic velocity distribution within the continent and other geophysical and geological information, as well as the orientation of plate movement of the Antarctic plate against hotspots that could reveal the tectonic history of the formation and breakup process of the supercontinent in the southern hemisphere. In contrast, a clear difference of dispersion curves between West and East Antarctica in the phase velocity of Rayleigh waves was obtained from the polnet data, together with a difference between the coastal area and the interior of the two continental terrains. Moreover, P-wave receiver functions demonstrated a detailed structure of the seismic discontinuities and mantle transition zones of the upper mantle beneath the West Antarctic Rift System, WARS, using the IP-retrieved data. A complicated distribution of the thermally upwelling mantle plumes was clearly identified. In addition, a shear wave isotropy analysis by using the polnet data in West Antarctica obtained the fastest splitting orientation for SKS waves, i.e., the strongest isotropic direction in the upper mantle, which did not correspond to the present plate movement, rather the extensional tectonic regime within WARS. However, a rather different oriented isotropy was achieved in the Marie Byrd Land, MBL, which reflected a past orogenic movement of the tectonic terrains. Seismic tomography uses the P-wave travel times of all the polnet data. Moreover, the heterogeneous structure of the upper mantle with wavelengths more than 1,000 km was clearly imaged with a high space resolution for the Antarctic continent, rather than those obtained from surface wave tomography. In West Antarctica, particularly under MBL, hot plumes were recognized down to a depth of 800 km. The polnet data were efficiently utilized in addition to the existing FDSN data. For instance, a very high-resolution three-dimensional shear velocity model was achieved for the upper mantle, both lithosphere and asthenosphere, of the Antarctic plate, by applying a multifilter technique to the surface waves generated by earthquakes that occurred at the surrounding plate boundaries, Figure 2. The tomography study imaged a lithospheric root in East Antarctica almost reaching down to a depth of 200 km, as well as clear boundaries to separate each tectonic terrain, geological fragments, within the continent. Moreover, low-velocity regions were clearly found to spread out surrounding GSM, which might reflect an existence of a deep crustal root beneath the mountains. 3D image of the upper mantle shear velocity structure by surface wave tomography from the AGAP/polnet data, modified after. Left, the 150 km depth slice for S-wave velocity distribution. Upper right, cross-section down to a depth of 200 km depth for the profile show, U, DOMA MCM, U. Lower right, cross-section down to a depth of 200 km for the profile SBA, S, DOMA ZHG, S. Copyright Clearance Center, CCC, http://www.copyright.com/ License number, 4,278,580,124,881, license date, January 30, 2018. As one of the tectonic regions in East Antarctica, the Lutso-Holm Bay area where the Japanese permanent station, Saiwa, has been situated, the upper mantle isotropy and seismic discontinuity were studied during the IB by using broadband seismic data distributed by the Japanese Antarctic Research Expedition, JRE. A long-period P-wave receiver function analysis demonstrated the heterogeneous velocity structures and distribution of upper mantle seismic discontinuities around the depths of 410 and 660 km. Moreover, a shear wave splitting analysis for SKS waves determined an isotropy of the upper mantle in LHB associated with the past mantle flows within the lithosphere-asthenosphere system and also a relationship with the tectonics of the region. Usui et al. Pointed out a possibility that the breakup process of the Gondwana supercontinent had affected both the formation of seismic isotropy of the continental margins in LHB and the generation of orientation distribution of the depths of upper mantle discontinuities of the region.